have any questions for the format? Very good. I will give the word to Jakub. Jakub is an intern at our company at the moment, and he prepared the presentation for today.
All right, so we don't have the echo. I will just first share my screen. Okay. Can you see? Yeah, you can see the presentation. All right, so my name is Jakub, as Bruno introduced me. I'm an intern here, and today the topic will be on something we still have a lot to work on, and we start to do that, which is invalid depth classification. And I will explain what we mean by that very soon. So to give some plan to what are we going to talk about first, before we move on to the discussion, is first I will explain what we mean by our problem. So what is the invalid depth for us and how that is a problem? What is our motivation to deal with it? So why do we have to actually handle and find a solution for that problem? And also how we dealt with it so far. Then some solution ideas that we've already generated and thought about for solving this particular problem. And also I would describe the current solution, or I would say a work in progress solution towards something that would satisfy our requirements. And in the end, as Bruno mentioned, there will be the discussion, so the clue of today's meeting. So if some of you will have ideas that could help us in solving this problem that we have at hand. So starting first with the definition of the problem. What do we mean by invalid depth? So in our use case, we have depth cameras, so cameras with two lenses that do some stereo matching to obtain the depth images of the scene in front of the camera. And you can see these depth images on the colored pictures here. This color coding is basically explaining the distance of objects in the scene. So the more red ones are the closest ones, blue ones are objects further. And what is the problem for us is this a lot of black areas. So these are the areas in which we call the depth measurement is invalid. And this is also what the manufacturer says for those areas. So in these areas, basically, we cannot tell what the depth is. This can be for several reasons. One of them is that if there is an object that is too close to the camera, there is some certain limitation of the device given by the manufacturer as well. So there is a certain distance. In our case, it's more or less 20 centimeters, below which we cannot measure the depth of the objects in the scene. And the second case is that if we have something completely different, so an object which is quite far from us, from the camera, and is very homogeneous in its texture. So this can be either a sky or a white wall that is far enough from the camera so that the infrared projector that is used also in this device cannot really overlay any pattern on the texture or on this flat surface and create some texture that would be useful for stereo matching. The other case also that is not listed here, but also happens, is the shadow that can be behind the object. So for example, like if we have something very close, like a hand here, and things in the back, there will be some area around the object, some shadow, in which we also have black pixels, so invalid depth measurements. Why do we need to deal with that? Basically, in our case, our obstacle detection, so something we want to do to inform the user of our device to avoid the obstacles, relies very heavily, if not only, on the depth information. So as good the depth information is, the same good our obstacle detection will be in a certain sense. So we would like to have a depth information that's as complete as possible. And we would like to, therefore, know what is in those black regions. The ultimate goal for us is mostly to know whether there are very close obstacles or not in front of our cameras, because we should notify the user in such case. For example, if someone put a hand on top of the camera or some piece of the clothing covered one of the lenses, because this will degrade any kind of performance of our device. And we need to let know to the user that something's wrong and maybe he or she should correct that. So given a region of these invalid values, there are several possibilities. What does it mean actually about the environment? First thing it can mean is, as I mentioned, can be a very distant object like the sky or a very homogeneous wall. And this is an area that we can safely ignore. I mean, safely to some extent, but we can ignore it because it's not something that will be an obstacle for our user. Second case is a very close obstacle, so something that's actually covering the lens. In that case here, it was a piece of, there's some clothes in front of the camera. And in that case, we want to inform the user for the reasons I've already mentioned. And there's the third case, which is I guess, will be the most problematic one in the end. It's these invalid values can arise from other artifacts in the scene. Probably one of the most important ones is a strong light reflection or direct sunlight, for example, in front of the camera. Because then actually we don't know. I mean, maybe this reflection comes from an obstacle that's close. Maybe it's from some surface like here, like ground, which we don't really care about. This is an extreme case of the problem we're dealing with. So the simple solution we've used so far is very straightforward. First, we take an image of that we've obtained as it came from the camera of the depth values, and we count how many invalid pixels there are. If there is a lot of them, so if they pass a certain threshold, we just simply assume there is a very close obstacle in front of the camera and would be able to notify the user accordingly. In other case, we would proceed with the obstacle detection, but ignoring the invalid depth area. So everything that's inside the black pixels, we would just simply not take into account when producing the results for the obstacles. So first, we try to generate some solution ideas for our problem. The first ideas were related to the hardware. So what can we do maybe with the hardware to improve the original depth measurements that we get? Unfortunately, there is, as far as we know, there will be still a limitation of this minimal distance that will be always something bigger than 0. This is because even if you change some setting of the device, there is some limited field of view for the cameras. You can also have the case in which you will see the object only in one camera, not in the two of them. So in that case, the depth values will probably not be computed correctly. The second idea that we had is, as we've observed in these black regions, we could have some characteristic noise patterns. So basically, they look like dots of some fake depth measurements, and we wanted to check whether this noise has some meaningful pattern, whether it differs for the objects that are far, like the sky, or the very close objects. Unfortunately, that was not successful. Later, we also explored another hardware-related issue that was because our cameras have the infrared projector, which is used for close distance objects. This projector creates some dots, as we could see actually on the image here. You could see like all these dots are coming from the infrared projector. So what we could do is that for the close obstacles, we would try to find this pattern in the image, and if we would find some, we would say, okay, this is probably a close obstacle. The problem is that these dots are only visible in the grayscale images only in poorly illuminated scenes. So that would work maybe in some conditions inside of the buildings, but outside in strong sunlight, they are unfortunately not seen. For the other solutions, we also thought about maybe we can do sky detection and segmentation, because sky is one of our big adversaries in this problem. It generates a lot of these black areas. So maybe detecting the sky and then eliminating it would be some sort of a solution. But after all, as we also thought, this is not our goal. We don't want to know where the sky is. I mean, this could in the end be a partial solution to the problem, but this is not the goal. We want to know where the close obstacles are, not where the sky is, and not eliminate maybe all of the other possibilities of the invalid depth values. Rather just focus on the obstacles. The other thing that we considered was because of the fact that the problem that we seem to handle, so covering of the lens, sounds like a problem of camera tampering, so something that surveillance cameras deal with when manufacturers want to know whether the camera that's set up somewhere to monitor an area is covered or damaged by someone who's trying to do some malicious things inside. But the problem here, what seems to be the problem in that case, is that in scenarios of the surveillance cameras, you can assume that you have a static background. And in our case, the camera is constantly changing its field of view. The user is moving, turning, and in general, our scene is quite dynamic. What we went so far with, and I will present that next in our in the current solution that we have, is to use simple texture characteristics of the corresponding grayscale image. This is actually still something that that works for cases where we want to differentiate between the sky region and the close obstacle region. But the problem here, and if we still continue with this approach, if we only rely on this approach, is that there is a lot of hand-engineered criteria. How do you compute the image features that are important, and how do you differentiate between these various cases, or how do you classify the objects just based on these hand-engineered image features? Another solution, this is the one that is yet to be explored, but is an idea that we surely will check out, is to use more information from the video, and so to use our assumptions, because in our cases, the close obstacles, first of all, we have the videos, so we have the sequences of images. We can know what was the previous frame, what is the next frame. We can monitor the change across several frames. And secondly, we know that probably there won't be a close obstacle that just materializes in front of the camera at the distance of 10 centimeters in front of the user. This must have been something that probably came from the side, one of the sides of the user, as this is probably some body part or a cloth, something that belongs to the user, basically. The problem here that it's still a lot of edge cases. For example, the sky, which is also always from one side of the image, usually on the top, and it will also move in a way that can be similar to the way the cloth covering the camera is moving. So this is still the solution that we haven't explored, but this is something that probably will improve the results of the close obstacle detection.
I have a quick question.
Yes.
I ask, like, if you go back 2 slides, yeah, basically, no, this one, where you say looking at the protected IR dots, but I mean, you're looking at the grayscale image, but you can't just, I mean, usually you can also just get the raw infrared image from the infrared, and from then you should basically always see those, and then just basically use the technique to sort of, if the area is really bright because it's highly illuminated by the infrared, then of course it can still be the glares and stuff, but why did you use just the grayscale image, or don't you have access to the raw infrared image?
Honestly, I don't. I'm not sure about, like, yes, we didn't try to access the infrared images. We would need to check if that's possible with the cameras. That would be.
Because I also like experiment with this a while back with like these kind of cameras, and I know like with some, I think you don't get the raw one, but with a lot of them you can also just get the raw infrared camera.
All right, that could be a solution. Yeah, definitely.
But wouldn't that suffer from the same problem? Unfortunately, I couldn't see the messages. Suffer from the same.
You mean the same as the grayscale image?
Suffer from the same problem that when when the dots disappear if you go outside and the image scene in itself is very bright, so that you can't ensure that. I mean, not being the expert on infrared images here.
Yes, I mean, of course, yeah. If you're outside, then probably because usually of the sun, it's like so bright. Then I mean, this would basically only be a solution for like indoor, I would say.
Not entirely either, I would say, because the spectrum of the sun is much weaker in the infrared than in the visible part. So in general, this should work. It should at least help. Like it can't fully solve every
You mean
problem.
what would help means is directly accessing the image
Yes,
from the
either
infrared.
having directly access to it, or if you can't manage it and if you don't need the visible information, use an infrared filter, which only lets through, or mostly only lets through infrared light.
But that would be a physical filter in front of the camera.
Yes.
Okay, but then the question is, I mean, this is just in one scenario where we want to, like, I would say in 98% of the cases, we don't care about this because there's no obstacle. And we just want to know these few cases where you actually stand in front of something that is super close. I mean, the thing you have to see here is that we're talking only about like areas between, I would say, 0 and depending, but 20 centimeters max. So everything that is like, that's the area which obviously you still want to know about. But the question is, if we put on the filter, wouldn't it like mess with the rest of the?
It depends on on how the camera works. I don't know this exactly, but if it only uses the information in the infrared area anyway, so if this information were sufficient, then this wouldn't be a problem. But yes, this is,
no, but I mean, the point is, I don't know if we I mean, the cameras are produced by Intel. I haven't really checked that option. Maybe if we have access to it, well, it's a good point, Fabian. We will see other things there. What I would suggest though is that before we do this, you just Jakub finishes the last part of his presentation. No, but it's good to ask questions, and then we can discuss this and see where this goes. Because I mean, the thing is, our current the current way which you will present already covers most of the things, but not all of them. So you will see and then discuss this afterwards.
Yeah, I think the fact that it covers most of the things is a bit of overstatement, but yeah, we'll get to that. So yeah, for the current solution, what we're doing is, as I said, we're basing our classification on simple image texture features. So in general, what we do is we look at what is in the grayscale image in the areas where there are black pixels on the depth image, so the invalid depth values. And what we use is glcm. I don't know if this is a very old image texture analysis technique. It stands for gray level co-occurrence matrices. In general, it's called also co-occurrence matrices method or tool. And from these matrices, you can compute several metrics, one of which is a correlation metric. And these metrics seem to differentiate between well, in our case, the clear sky and the close obstacles, which are a bit different than something as homogeneous as the sky. And this is based on this linked scikit image tutorial here. And I will just quickly go through like how this algorithm works for us. So if we have this example on the left side, we have our depth image for this image, grayscale image on the right. What we first do is we downsample this depth image, so we create this kind of big pixels of depth values. And now we will be dealing only with the black area, so the invalid depth area. From this area in the grayscale image, we sample this certain number of these superpixels, so of these superpixel areas. And for these areas, we'll compute the glcm matrices and then the correlation metric. So to very quickly explain what the glcm thing is, it's used as a texture characterization tool. What you do is you define, the whole idea of the thing is to compute how pixels in a certain configuration happen together. So what I mean by that is how, for example, a pixel with intensity value 1, how often is it together with a pixel of intensity value 5 at the distance of 2 in the horizontal direction, for instance. What we can change is this horizontal, it can be a horizontal direction, can be vertical one, can be a diagonal one, can be even something more complicated. This is up to the choice. For each of those configurations, there will be a co-occurrence matrix created. And in this co-occurrence matrix, what these values basically say is, for example, if you would have only 5 grayscale levels, in a normal image we would have 256, but for simplicity, let's say we have only 5. So for example, what this value 2 says is that the pixel of the with the value intensity value 1 co-occurred with the pixel with intensity value 3 at this configuration 2 times, and with the pixel value 5 5 times, and with the pixel of the same value 7 times. And for each of these configurations, we get basically this kind of square matrix. We can specify several of those configurations, and after that, we can compute some of the GLCM metrics. One of those metrics is not important, like how the math here, but it's this correlation metric.
Hallo.
Which
Ich bin gerade noch auf der Arbeit. Ich rufe dich danach zurück, ja?
Seemed on the set I was working with for experimenting with this technique.
Bis später.
Differentiate between clear skies, which is kind of homogeneous, and the close obstacles, which are more varied in a way because of usually there's some objects such as the hand or clothes. So this is not as uniform as the sky. So some first results that we obtained at the time are here. So this is on the set I was working with. The blue areas you can see is something that was classified as sky, and red is are close obstacles. So something or obstacles in general, not necessarily close. In these cases, it worked quite promisingly. So we also did it on the separate set. We've selected also still quite small. It was 49 images. And here I've shown some of the examples from that set, some of the correct ones. So on the left side, we have correct sky region classifications. On the right side, correct close obstacle classifications. But of course, this method is not ideal, or still very far from that. Those are the examples of these bad classifications. So some cases in which the sky was considered to be an obstacle, or vice versa, when an obstacle like this one very close, but as you see, it's very illuminated. Which was considered as the sky. So just to give some numbers for this for this approach, we've also done some. There are 3 hyperparameters we had to choose there, so we've done, I guess, some simple hyperparameter search, and for the best configuration, the best achieved result as measured by the F1 score was as following here. And obviously, what we would want to achieve is something that has much higher recall, because we want to pick up all of those close obstacle cases, or nearly all of them, for the user, so to inform him or her every time something is covering the camera, and also still keep quite a good precision, because you also don't want to alert the user when there is no need for that. So that would conclude this part of presenting what is the current state of the solution for us. And right now, I guess we will move to the discussion part. So can you help us? Can you have some other ideas of solving this problem, as we already started to actually discuss?
So if I understand it correctly, you're looking if the basically how uniform, so to speak, like the invalid area is,
yes.
And then determine if it's basically to take this as the sky. However, if the obstacle in front would also be that uniform in what you're,
then there is a problem. Yes.
Yeah. So I mean, but for example, in the case, right, if you like also in the case where you showed the ones where it didn't work, where you exactly where the front object was basically too illuminated too strongly, so to speak, right? If it would be possible to get the IR image, right, then these cases, I guess you could solve by basically just looking at how bright the area is, and basically if it's really bright, then you just, okay, this is a close object. The only other sort of edge case where it of course would fail is the potentially some kind of glare or so, or like some external IR source, which is of course is picked up.
That is unlikely, I guess. Yeah, but yeah, still the case of the direct sunlight, as you mentioned, like a very glaring object or reflection, this would still be considered as very uniform. And yeah, this was actually, I think, the first thing where we noticed that. I mean, where you look at the users will be using it also a lot outside, so they will face a lot of directions, and I imagine many times it will be in front of the sunlight.
I have like one also more technical, maybe a solution idea for this, like for the glaring reflections and direct sunlight. Like if you use a polarizing filter for the camera, like because direct sunlight will be often polarized and strong reflections definitely are, you can reduce the reflections a lot. So then you get clearer images. It depends a bit on what camera you use and what you can get to fit, but this is a very simple solution. It's a tiny thing that you can just mount on your camera.
Just out of curiosity, so we'll work on this setup. How much, do you know how much these filters are and how big they are?
In money? No, not expensive. It's a very cheap thing. Like I think like 50 euros or something like this. You can get one.
Like you can get. I guess you can get them in variable sizes, right?
You can get them for every kind of setup that you might want, and you could technically probably also build it yourself if you felt like it.
I mean, isn't that just what if you go to this 3D cinema, right? This is kind of.
Yeah, this is like, for example, one thing. Take the lens of the.
Just go to the cinema, you get one for free.
Yeah, true. I used one actually in an experimental setup for me. I missed one, and so I just took the glasses from the cinema. And they don't have like a very high efficiency, but you don't need a perfect scientific efficiency. You just want to improve the images a bit. So this for like direct reflections and direct sunlight, this helps a lot.
Okay.
Yeah, if nothing else helps, I would also just try letting a computer do it. So like having a model, you basically just find out where all the regions are that are invalid, right? Maybe try to find boundaries around them, and then you give that as an input to a model and let that one decide whether it's a close object or not. Maybe they can see something that you don't, because there are patterns or something, but they are in such slight variation that you don't really see them in the image, but a computer would still be able to make out the difference. But since you need to label for that and everything, I would just try that as a last approach.
I think that's the thing. Is we talked about it last time. I think there are two problems here. One is we don't really have annotated data for this. We could get some, but I guess it's not easy and not cheap. And then the second thing is also the computing time it takes to run this is limited. I mean, one idea I had anyways in like the greater scheme of what we're doing at the moment is to probably at one point, but that's like future, is we have a very basic object detection model. And the question is if we cannot use, given we had the right data, predict more than just bounding boxes out of this central model, where it would be some sort of a multitask learning approach. You share the features that at the input, and then you have probably multiple heads which predict different things. I've seen that work for autonomous driving quite well. The question is, can we scale it down so that it actually works on our hardware, and can we make it work with not having, I don't know, 500,000 for data annotation? And so that would be one question, but that was one thing on their side anyways that I was thinking. but we're looking for something easier at the moment. I really like the idea that Fabian had, saying, okay, we take the approach we have right now and then work on those cases where it doesn't work. But yeah, generally, I think there are still like so many things that we haven't considered yet, where I'm not sure. I mean, one other thing was something like we engineer a few more features and then train something a lot smaller, like some random forest where you need less data than a huge deep learning model, right? So you could do something like handcraft some features, maybe use the GLM, like those matrices that Jakub's computing at the moment, and then combine it with some other handcrafted features and train some random forests on this. But there, the question would also be, what are those features that actually give us the kind of information that we want? What is so specific? And that was the main thing we were thinking about. What is so specific about, like, what would differentiate a close obstacle from sky?
I mean, like, I have like another idea.
Yeah, sure.
It's basically also how we do it, right? You basically just have two cameras, so you have stereo vision, right? And then you basically have two cameras, and so basically the thing is that, of course, objects that are really far away, they are in both images, they're going to be basically in the same place, but really objects that are really close by will be completely different in the two images. And basically,
I mean, this is already a stereo setup, and the matching is like the depth images that we receive are a result of that stereo setup that with the software from Intel. And it's just I think the invalid depths are those cases where this matching actually fails due to the fact, and that's where it comes in, that you can't separate between very far and very close.
But then I would expect
but
that
I
you
mean,
get...
if you have the raw information, basically, right? If you just get this raw data, basically not after it's already processed by the system, then like I think they probably just throw it away because they can't give you accurate data about these things,
Yeah,
right? Because they can't really guarantee like the resolution that they have for the range where it works. But I think from that you should still basically be able to basically just make a distinction. Okay, this is too far away, or this is like too close. I think that should be possible.
I mean, that sounds also like two different error cases for them, right? Like if you said it's like a closed system, the two cameras, and they just give you back the depth image, you said, right? So, but when they calculate it, I mean, one error case is you see something in one image that you don't see in the other image at all, right? So that would be, for example, something that's probably too close. And the other error case is where it's so far away that it's exactly matching in both images, right? So there can be made an argument to say, okay, this is there.
No, totally. The problem I see is, I mean, the cameras at the moment are probably like a centimeter away from each other, probably a bit more.
4 centimeters.
And I'm pretty sure that something that is close will still appear in most of the time in both images. The question is, they will be different, right? That's true. You're right, Fabian, in the sense that I guess there will be a difference, but the question is, how can we quantify that difference to the point that we can be sure that it is actually a close obstacle? And then the second question is, I was hoping to find something that actually works on the results we have, so that we just save computation. I mentioned it a few times.
I mean, like, for example, you could of course focus on the sort of the case, because I think the case to determine if it's basically far away, for like the sky or so, is easier, right? So you could of course do the inverse, right? You basically say, okay, is this a far away object? And if it's not one, you assume it's close.
Yeah.
Right, and there you basically just would have to, I guess, match, like basically have sort of two images, and if they basically match up to a certain extent, then I would say this is a far away object. Otherwise, it's close.
But you talked about this in your slides as well, right? That you didn't want that approach because you were not sure that the sky is really like the only thing or something. You had sky detection as a bullet point on one of your slides.
Yeah, I mean, we more drop it because like we thought that, okay, I mean, the sky detection is not our goal. Like we don't want to know. Maybe it's a sub solution to that problem, like detect sky and then remove it from the results. But also like coming back to what you said before, because I think that even if we have, let's say, these raw images, like 2 raw images, from the cameras, and we do this distinction whether something's far or close on our own. I think for some cases you still cannot tell, because let's say there is something very far, it's very uniform, so you couldn't even match it on the image. And now the question is, couldn't you match it because it was in both images but very uniform, or couldn't you match it because there was something in one image and was not in the other, which would be the case in the close case? And you didn't match it because of that, because the object was not present in two images. So I think there is still like this problem, even though if we do the matching on our own.
I
But,
unfortunately
if I
leave
may-
now, so have fun. Bye.
Oh, bye.
Like one other thing, of course, could be to just extend it by basically having sort of a close range, what is it?
Proximity sensor.
Basically sort of, for example, like a laser-based thing or so, which basically exactly measures like how long the laser took to basically come back or so.
Yeah.
Basically have that, of course. Or use something like a radar or something, or whatever there is, I guess. I think that's what they also use for like cars or so, to like do these close range stuff.
Yeah, I think the problem with LiDAR would be in general nice for getting a very good depth image. I think that's also the case, but we don't have it. I don't know also how it would be like, since this is a worn device, something portable. I don't know how energy efficient having a LiDAR there would be, because that's probably quite energy. Well, yeah.
I think there was another idea.
I was just making a remark on you were saying that you stopped doing the sky detection, but it might not be so bad in the end, because if you remove the sky beforehand, like you do some simple object segmentation on the image, and then you first remove, meaning the person wearing the thing will be outside most of the time. So first, if you remove the sky, you make disappear a quarter of the image, so it's faster processing later. But also, you can also continue using the conformity matrix and tweak the parameters so it's more sensible to differences on ground objects. If you just, because for now the conformity matrix is also working on the sky, and so you have big differences because the sky is very uniform and objects on the ground are not so uniform. But the conformity matrix are made so they can detect both sky and object on the ground. But if you remove sky beforehand, maybe you can have it work better. I don't know.
I see that. Yeah, I mean, I think that I agree. The question is, can we detect that? First of all, we need to remember we have a grayscale images, so it already makes detecting sky a bit more difficult because you don't have color information. So everything that's one colored in a certain intensity, looks like a sky a bit. But yeah, the question is, is there some sky detectors, let's say, or detection that is good enough to? Yeah, I mean, I've seen we've seen this detector which was supposedly working quite well. We didn't go into that direction. Maybe some more work on that would be, as you say, helpful, especially for this tweaking the parameters later on. Restricting the problem between these.
It doesn't even have to be specifically a sky detector. It can be just image segmentation, basic, and the top part of the image most likely will be the sky.
Yep.
I mean, you also talked about ground plane detection last time. maybe you can, like, I don't know, try to find out the plane of the sky as well, let's say, if you find out where invalid areas, but this is just conjecture. But another thing that's also just conjecture that I wanted to say, which might be an approach that is more add-on to what you currently have. In your presentation, you presented some of the cases that where it wasn't working, right? And what I noticed a little bit is that the edges of the area where it is an object in the foreground was kind of fuzzy because it was so close that the camera can't like really focus and stuff, right?
You mean for the incorrect classifications, right?
Yeah, for example, this one, yeah. And maybe you can find some argument with the edges here, because when the sky is so far away that you see really at the edge of the buildings, for example, it's quite clear edges, right? And for all the other cases, of course, that doesn't count for the glare where you don't have a clear edge. But at most contact points of the sky with other geometry, you seem to have these clear edges. And for your hand, for example, okay, it's also moving, and that is something else to take into consideration if you move, whether everything will blur or something. But yeah, maybe in that direction that you try to analyze the borders of the area and not the texture of the area. Maybe there might be something there as well.
Yeah, sounds really good. Yeah.
But the problem you have only happens when an object first appears, right? Because otherwise, if you have seen the object before, you're tracking the objects.
Yeah, we're tracking currently at least we're tracking only the objects that are detected by the object detector, right? So ones that are also classified, and there's a certain number of classes we use. So for example, I mean, we don't detect, unless the hand would be somehow detected as a person for some reason, which could be, I mean, it's could be the case, but yeah, not everything is tracked. Like some of the objects that appear, like something like this, will not be probably tracked because it won't be also classified by the object detector to be any of the classes we use, unless we at some point also extend the set of classes, and this would be possible to classify this as cloth, for example, or yeah, jacket, I don't know. So the problem with tracking is that not everything is tracked. Only the object detection results are tracked, and object detection results are restricted only to several classes.
Yeah, okay. I see.
Yeah, but like anyway, the edge detection might be a good idea anyway for also segmenting the regions of invalid depth pixels into different regions, basically, right? So if you have like a very close obstacle and the sky is directly behind it, what then, right? Because everything will be invalid, and just from the depth information you can't really make out the edges of objects anymore, and that way maybe
Yeah, sounds very good, thanks. Yeah.
Okay. Yes. I mean, there are a few ideas.
Yes, sorry.
I'll go home next time and I'll do it from there. So there are a few ideas I think that are good. I really like generally, I think what we'll definitely try is access the raw data from the camera and see if that's actually possible. And then also the polarization filter. Yeah, I think that was the point of today's meeting. I don't know. I don't know if the ones that have been there last time basically just started at the moment, I think. Jakub, if you like that less presentation, more discussion, or if you would have like a presentation as well, a bigger presentation, just to get feedback, or the others, just in general, do you like the format like this? Because I mean, the point is here not to create this to solve bipeds problems. So it's not supposed to be, hey, you all are free advices, but it's supposed to be something where I mean, different people can present something, and like everybody can get something out of it, learn something, I hope, and then have this as an interesting thing. So I would like to update the format to something that everybody likes, and then also maybe if we've moved onto something that we like move it to a bigger audience maybe later. But that's something still to be discussed. So if you have some direct feedback now, I would be happy to hear it. If you have something later, just send me a message. And I mean, first of all, thanks for coming. Thanks for discussing it with us. And also the invitation to everybody, if you have something you want to present or a problem you want to talk about that you have, wherever it will be, let us know, let me know, so you can do that next time. And I will see if we find maybe somebody else otherwise to present something next time. And yeah, that's basically it from my side.
I liked the format a lot more this time around, because it was, I think, there was only one question this time during the presentation, right? And it was more orderly this way, I think. Because last time it derailed because the presentation was long and stuff, but no.
Okay. No, that's good. That's good. Yeah, then I think what I would do is maybe if you have somebody in mind that could have an interest